Hi viewers, welcome to my class on mechanics of materials. In today's class, we'll draw the shear force and bending moment diagram for an overhanging beam subjected to uniformly distributed loads and point loads. This is an overhanging beam supported at A and B and subjected to UDL in the portion AD and BC. So the intensity of UDL in this section is 2 kilonewton per meter. So that means every meter length 2 kilonewton load is acting. So the resultant load will be 8 kilonewton. 2 into 4, 8 kilonewton. And here you have a point load 6 kilonewton. Here again at the E you have 3 kilonewton point load. And this portion BC is subjected to UDL of intensity 3 kilonewton per meter. So the resultant load of this is 3 into 2, 6 kilonewton acting at the center. That means from B 1 meter and from the support A it will be 11 meter. This is totally 10 up to B and then another 1 meter, 11 meter. So you have to draw the shear force diagram and bending moment diagram for this beam. First step is to find out the support reactions. So to find out the support reactions, you can take the moment summation with respect to point A. Now when you take the moment summation with respect to point A, the resultant load due to this UDL will be acting at the center and at a distance 2 meter away from A. So 8 kilonewton acting at a distance of 2 meter. So that will produce a clockwise moment. So 8 into 2, that is a moment produced by that resultant UDL, plus 6 into 4, this is producing clockwise moment, so 6 into 4, plus 3 into 6, this RB will be producing anti-clockwise moment, so minus RB into 10, plus this 6 will be producing a clockwise moment, and the distance of the resultant load is 10 plus 1 meter, so 11 meter. So 6 into 11, that summation will be equal to 0. So that is the summation. 2 into 4, that is the resultant load 8 into the distance 2 plus 6 into 4 plus 3 into 6 minus RB into 10 because it's anti-clockwise moment, minus RB into 10 plus this resultant load is 3 into 2, 6 and the distance is 10 plus 1, 11. So that summation is equal to 0. So from that you get RB as 12.4 kilonewton. So you are getting this support reaction 12.4 kilonewton. So once you get this support reaction, you can find out the other support reaction. All loads are vertical. So total resultant downward load you can calculate, and this is 8 kilonewton plus 6, 14 kilonewton plus 3, that is 17 plus 6, 23. Total downward load is 23 kilonewton. Out of that RB is sharing 12.4 kilonewton. So remaining 10.6 kilonewton and this support has to take. So the reaction at A, support A is 10.6 kilonewton. So you can find out the total downward load and subtract the reaction at the other support B. So which will give the reaction at the support A. So 10.6 is the reaction at A. So we got the reaction at A and B. Now you can make the shear force calculation. So the reaction I have shown here, when UDL acts, shear force will be varying continuously. So you need to take two sections to calculate the shear force. In wherever UDL is acting, you have to take a section left end of that portion and right end of that portion. Not exactly at the end, a little away from that end A or the end of that UDL, and again a very small distance away from the other end of the UDL. So 2 sections you should take. At the ends, 2 sections, you calculate the shear force and then you can show the variation of shear force. So wherever UDL comes, you have to calculate the shear force at either end of that section which is subjected to UDL. So immediately right of A you can calculate the shear force, and immediately left of D you can calculate the shear force. Similarly here, immediately right of B you should calculate the shear force, immediately left of C you should calculate the shear force. Now other sections D, it is going to be constant. You have to take only one section and calculate the shear force. And here in the section EB also you have to take one section and calculate the shear force. So wherever UDL or UVL comes, you have to find out the shear force on either end, not exactly at the end, infinitesimally small distance away from the end in the UDL part or UVL part. You should calculate the shear. Now let us take a section immediately right of A. Immediately right of A means infinitesimally small distance away from A. So this UDL part you can neglect. Okay, very small part of that UDL is included, so that can be neglected, and you get the shear force as 10.6. okay, so this is a section which I have taken immediately right of A. Now the shear force, this part of the load is only this reaction, so 10.6 kilonewton is the shear force. So immediately right of A, shear force right of A is 10.6 kilonewton. Now if you take a section immediately left of D, shear force is 10.6 minus this part of UDL, complete over the complete length, the UDL will come here, and when you take this section you have to take the resultant UDL, the total UDL you should take. So 2 into 4, 8 kilonewton, which is acting downward, will produce a negative shear force. So 10.6 minus 8, that will be the shear force at this section. So 10.6 minus 8 is 2.6. I have taken a section here. Now calculating the shear force, 10.6 minus 10.6. I am just seeing the loads on the left part. 10.6 minus 8. This complete length UDL is there. This is only very small distance away. So 10.6 minus 8, which will give 2.6. Now next section is DE. So here only point loads are acting. So you have to calculate anywhere in the section DE. It's going to be constant. The shear force is going to be constant. So anywhere you can calculate. So let us take a section, sum of the forces. Okay, sum of this shear forces. 10.6 minus 8 minus 6, that will be the shear force in the section DE. So section DE you can take 10.6 minus 8 minus 6. So 10.6 minus 8 minus 6, so it will give minus 3.4. So or whatever previous section you had, no, here previous section minus 6. So this is the shear force for the previous section, minus 6, that will give this value. Whatever load is added after the previous section we have taken, this was the previous section, here was the previous section, and from there when you move to the next section, this load is the addition. So it is producing negative shear force, so minus 6. So we had a shear force for this section 2.6, minus 6 will give minus 3.4. Next section you can take EB. Here also shear force is going to be constant. Now in this section shear force, whatever shear force you add for the section DE, minus 3 will be the shear force here. So this minus 3 or minus 6.4, that will be the shear force for this section. You can sum up all these forces, which will again give the same result. 10.6 minus 8 minus 6 minus 3, that will give the shear force for this section. But this summation is already there. We have already done that summation for the previous section. and when you move to the next section you have to only subtract 3 because it's a downward force. Subtract 3, which will give the shear force for this section as minus 6.4. So that is 10.6 minus 8 minus 6 minus 3, or minus 3.4. This value is minus 3.4. You already know that minus 3 give minus 6.4. Next section, UDL is acting. So immediately right of B you should calculate. Immediately right of B you calculate. So immediately right of B, the shear force including this 12.4, that reaction you should take. Okay, this reaction also you should consider because you are just away from B. So all these forces summation plus 12.4 will give the shear force here. So you have already summation of these forces here, minus 6.4 plus 12.4, so that will give 6 kilonewton. So you can sum up, so this is a section, you can sum up all the forces, 10.6 minus 8 minus 6 minus 3 plus 12.4, or already this summation is here, minus 6.4 plus 12.4, which will give 6 kilonewton. When you come to the next section, left of C, even left of C and C it will be same, but the common practice is to take on either end. It will be same at the C also because no point load is acting here. Now calculating the shear force, so you have a shear force immediately right of B 6 kilonewton. Okay, here you have 6 kilonewton. That is a summation of all this minus this part of UDL. So it is for the entire length. So 3 into 2, 6 kilonewton downward. So here you have plus 6 minus 6, which will give 0. So you can sum up from left side all this, but already you have this summation, minus 6 will give the shear force at this section. So this total is 6. You already have that summation, minus 6 will give 0. That is the shear force left of C, and there is no load acting here. At C also it will be 0. So immediately left of C and C you will have the same value because there is no load. This is only negligibly small distance. But other points like this, if you take a section here, this section, and immediately say for the section D, there is a difference because point load is acting here. So there will be a difference for this section left of D and for the section D. Next, let us calculate the bending moment and at salient points. We know that bending moment at extreme ends is going to be 0. So at A, bending moment is 0. Unless you have a couple acting here, the bending moment at ends will be 0. So at A, bending moment is 0. Since there is no load acting here, left of A, and there is no moment produced by these loads. Okay, no load is acting, only one load is acting here, and that will not produce any moment. So the bending moment at A is 0. So you can write bending moment at A is 0. Next, bending moment at D. To find out the bending moment at D, when you look at the left side forces, there are two forces, 10.6 and also this 8 kilonewton, that is a resultant of UDL, which is acting 2 meters away from this point D. Okay, so 10.6 will produce a clockwise moment, 10.6 into 4, 8 will produce a anti-clockwise moment because it's a downward. It will produce, when you consider left side, downward force will produce negative moment. So 8 into 2, that will produce a negative moment. So the bending moment at D is 10.6 into 4, 10.6 into 4 clockwise moment, and 8 into, that is 2 into 4, 8 into the distance 2. So that will give the bending moment at D as 26.4 kilonewton meter. Next, bending moment at E you can calculate. Bending moment at E is going to be 10.6 into 6 so this is producing clockwise moment, and again 2 into 4 8, 8 into the distance from E is going to be 2 plus another 2, so the resultant load is acting here 8, 8 into 2 plus 2, that is 4 meter. So downward force produces negative moment with respect to this point E. So bending moment at E is 10.6 into 6, so 10.6 into 6 minus 2 into 4, the resultant load 8 into distance is 4, minus this is also producing negative moment, minus 6 into 2. So the total is 19.6 kilonewton meter, that is bending moment at E. Next you have to calculate the bending moment at B. You have 10.6 into 10 meter, okay, total 10 meter, and this 2 into 4 8, 8 into the distance is 2 plus 2 plus 4, so that is the distance of this load from the moment center B. So totally 8 meter, so 2 into 4 8, 8 into 8, so that will be the moment, and it is negative moment. Next load is 6 kilonewton, 6 into 6, it is anti-clockwise moment or negative moment, so 6 into 6 will produce a negative moment. 3 will produce a negative moment, or minus 3 into 4, this will produce a negative bending moment with respect to point B. So 10.6 into 10, minus 8, 2 into 4 into total 8, minus 6 into 6 meter, minus 3 into 4 meter, so totally you get 6 kilonewton meter. That is a bending moment at B. And bending moment at C is 0, and that is extreme right end, and there is no couple there, so bending moment at C is 0. Now to know the nature of variation, let us take a section here and calculate the bending moment. Now if you check the shear force, what is the shear force for this section? 10.6 for this section, shear force is 10.6 minus 2x. This part of UDL you should take. So when you take a section, this is a considerable part of the load. So if it's very close, you can neglect that. So when it is at some distance away from the end A, this part of UDL you should take in calculating the shear force. So 10.6 minus 2x will be the shear force, and that is the equation for shear force, and that equation shows that is a linear variation. So shear force will vary linearly at 10.6 here, and at this immediately left of T it will be 10.6 minus 8, 2.6. So from 10.6 to 2.6 the variation is going to be linear, because we understood that at a distance x the shear force is 10.6 minus 2x, so that is a straight line equation, and shear force has to vary linearly. So from 10.6 it should go down to 2.6 linearly, so that will be the variation of shear force. So the equation for shear force is 10.6 minus 2x. Okay, so this is a straight line equation, and if you substitute x as 0 you will get 10.6, and x as 4 meter you will get 2.6. So this is the equation for shear force for the section AD. Any section in between A and D you can calculate the shear force using this equation. So I written this equation only to show that the variation is linear in this section. Shear force variation is linear. It gives a straight line equation. Now bending moment you can calculate for this section. Bending moment will be 10.6 into x. This will produce a clockwise moment. 10.6 into x, and this part of UDL is 2 into x, 2 kilonewton per meter for x meter. So 2x is the load, and that 2x load will act at a distance of x by 2. So this is x meter, and the resultant load will act at x by 2 distance away from the section, or x by 2 from here. The resultant load is at a distance of x by 2. So 2 into x, 2x into x by 2, that is the moment produced by this. 2x is the load into x by 2 is the distance. So bending moment is 10.6 into x. The load is 2x. The distance is x by 2. Center out of that part of UDL is at a distance x by 2. So 2x into x by 2. So that will give 10.6x minus 2 cancels, x square minus x square. So this is the equation for bending moment for this section. Anywhere between x value changing from 0 to 4, this equation is valid. So if you put x as 0, you get bending moment at A, that is 0. And if you put x as 4 meter, you will get the bending moment at D. Okay. So we already got the bending moment at D. You can check by putting x as 4. When you substitute x as 4, you will have 10.6 into 4 minus 4 square or 16, so which will give 26.4, the same value which you have got earlier for the bending moment at point D. So this equation I have written to show that the variation of bending moment and bending moment variation is parabolic, because you have x square term in this, so it is a parabolic equation. So bending moment variation is parabolic, so you should plot by a curve. So the bending moment is varying from 0 to 26.4, 0 to 26.4 at D. So the variation is going to be parabolic variation, a curve. You have to plot it by a curve from 0 to 26.4. So the shear force is going to linear variation. It's continuously decrease due to downward UDL. It will always continuously decrease, linearly decrease. So straight line variation for shear force. And bending moment when you plot for this section should be parabolic. Shear force for this section is immediately right of P, it's 6, and it changes to 0, 6 to 0. It's going to be a linear variation. For bending moment for this section, it's varying parabolically, and parabolic variation you have to show by a curve. And here at B you have minus 6, and at C you have 0. So minus 6 to 0, the variation you have to show parabolically like this. Okay. So that way you should plot for the sections where UDL is acting. So let us plot the shear force and bending moment diagram. Immediately right of A you had calculated 10.6. Immediately left of D you know 2.6. So right of A to left of D you should join. So 10.6 to 2.6. And for the section DE you know it is minus 3.4. That you can plot. So that point D, left of D to right to left of D, when you move to the next section, shear force will suddenly change at that point where point load is acting. So wherever point load acts, the shear force will change. If it's a downward force, shear force will decrease. If it's an upward force, shear force will increase at that point. So for the section DE we know 3.4 minus 3.4, so you can plot it by a constant value. And here the variation is from right of A to left of D. So that is the variation you have to show, 10.6 to 2.6. Next for the section EB it is minus 6.4, it is constant. So you can plot it by a horizontal line. Then at point B there is a change because it's a point load is acting. Or immediately right of B you know, immediately right of B it is 6. So that you can plot. For this section it is 6 to 0, linear variation. So 6 to 0 is here, and here this section it was minus, in the section EB it was minus 6.4, Whenever a point load acts, it immediately has to change, and we know immediately right of B the shear force is 6, so it has to change from minus 6.4 to 6 at point B, because immediately right of B you have 6, and immediately left of B, that is in the section EB anywhere, it is minus 6.4. So minus 6.4 to 6, it has to change at point B, minus 6.4 to 6, then to 0. So this is a variation of shear force along the length of the beam. Now in plotting the bending moment curve, you have parabolic variation for this wherever UDL is acting. So bending moment at A is 0, bending moment at D is 26.4, and the variation is parabolic. You can show that it is parabolic variation. So it is a curve, it is not a straight line, it is a curve, and this portion and these two sections you have constant shear force and only point loads are acting. There is no load in between, so you can plot it by linear variation, and we have that 19.6 at E. So from 26.4 it decreases to 19.6, and the variation is linear. Wherever shear force is constant, bending moment variation is going to be linear. Here shear force is constant, bending moment variation is linear. So this linear variation, it is from 19.6 to minus 6 at B. From minus 6 it goes to 0, and the variation is parabolic variation. This is a bending moment diagram showing the variation of bending moment along the length of the beam. Now we obtained the shear force diagram and bending moment diagram. Now in this bending moment diagram you can observe that bending moment is changing its sign at this point. So it is changing from positive value to negative value in this section, in this particular point. So this point is known as point of contraflexure or point of inflection. And if you are to locate this point, if question is asked to locate the point of contraflexure or point of inflection, then you need to find out the distance from any one of the end, like either left end this distance or from right end, and you have to mention that the distance from the left end is so much. So to locate this distance, first identify which section you are getting this point of contraflexure. This point is coming in the section EB, and this is a bending moment diagram, and so for the section EB you write down the bending moment equation. So for the section EB you can write down the bending moment equation and then equate that bending moment to 0, because this point bending moment is coming to 0. So let us write down the bending moment equation for that section. So I am taking a section here at a distance x from the left end. So my intention is to find out x, at what distance x this bending moment is coming to 0. So it may be like very close to 6 meter or nearer to B, that is 10 meter. So x can be from 6, that is at E, to B, that is 6 to 10. The validity of x is 6 to 10. So if you write the bending moment equation, you have this reaction is 10.6 into x, okay, and this force is 8 kilonewton. The resultant load is 8 kilonewton. Now from 8 kilonewton the distance is, total distance is x, you have to subtract 2 meter. This is total is 4 meter. The resultant load will act at a distance of 2 meter. So 8 into the distance is going to be x minus 2, total x minus 2, so that will be x minus 2. So 8 into x minus 2, 8 into x minus 2, and again 6 into the distance is x minus 4. So this distance is, total is x minus 4. So 6 into x minus 4, and 3 into this distance is, total is x, you have to subtract 6. So 3 into x minus 6, so minus. and downward force will produce a negative moment. So this is the bending moment equation. So 10.6x minus 8x plus 8 into 2 16, minus of minus plus 16, minus 6x minus of minus plus 24, minus 3x plus 3 into minus 6 plus 18. So we get minus 6.4x. all these constant if you add you will get 58, and you can solve x as 9.0625 meter. So this is the distance at which bending moment is coming to 0. So x is the distance at which this point of contraflexor occurs is 9.0625 meter away from the left end. So you may even use the similar triangle method to locate this point. These two triangles are similar, and you can use 19.6 divided by this. If you take it as d, 19.6 divided by d is equal to this 6 divided by this distance is total is 4 minus d, total is 4, and if you take this as d, this is going to be 4 minus d. So 6 divided by 4 minus d. So 19.6 divided by d is equal to 6 divided by 4 minus d, and from that you can find out d, and once you get d you can add 6 meter to that, which will give the point of contraflexor. That method also you can use to find out the point of contraflexor, and that is possible only when you get the bending moment variation linear. So somewhere in the parabolic section, when the bending moment changes its sign, then you cannot use this method. You need to write down the bending moment equation. So that's all for today. Thank you for watching.